All right, let's start it. Hello, everyone. My name is TJ from Virginia Tech. I'm an assistant professor at Virginia Tech, so welcome to my software special course at SKKU. So let me first introduce about myself and the objective, the goal of this course, and briefly going to talk about the first part of this course, which is DNS and DNSSEC. So let me first introduce myself. My name is TJ Chung, and my name is Taejung in Korean. I am an assistant professor at Virginia Tech, and I am an internet security and measurement researcher. I am mainly focusing on public key infrastructure. If you're not familiar with public infrastructure, it is fine. I'm going to walk you through all the details, so please don't be scared. So we're going to learn everything about public key infrastructure, not everything, but most of the part of the internet security protocols. So I'm currently work as a research fellow at Manners, mutually agreed norms for routing security. This is the organizations to improve routing security over the internet. And I received some multiple awards from top conferences as well as the IETF, IRTF, and also from a funding agency in the United States. And also published lots of papers in security or internet measurement conferences. So what are we going to learn throughout this course? So we are going to mainly focus on secure internet protocols. Then let me first talk about the internet protocols. The prominent example would be HTTP, right? You open your browser and you type a domain name and you will see a bunch of contents, right? So that is done through HTTP protocol, hypertext protocol. And this is the most well-known protocols that you use every day, not only for web browsing, but also whenever you watch some streaming such as Netflix or YouTube videos, all the traffic actually coming through HTTP protocol. But the problem of this HTTP protocol is it is not secure. This protocol was designed about nearly 50 years ago. And then at the time, all the functionality, all the focus of the protocol was just focused on just functionality, right? Just all the efforts were made to make the protocol work, right? Because of that, at the time, the security considerations were rarely made, okay? Because of this reason, HTTP was just designed as a plain text protocol. So anyone in the middle of the communication path, so let's say you two entities, client and servers, are communicating each other using HTTP protocol, then any man in the middle entity between these two communication paths, they can see what kinds of requests and the responses and the contents are through on this HTTP channel. Okay? So because of this reason, HTTPS was proposed nearly 25 years ago, 25 years ago, and HTTPS protocol plus a bunch of extensions like CRL, OCSP, HKPK, HSTS, CT, and other numerous protocols were added on top of HTTPS. If you're not familiar with the terminology, of course you are, it's completely fine. So I'm gonna walk you through all the details of these protocols in the HTTPS session. DNS, domain name service. This is all considered as another layer of the protocol. So what it means is, so if you ever taken a computer networks class, you must be familiar with the 5-layer or 7 OSI layers. So when you say just the 5-layer, it says physical link layer, IP layer, and the transport layer, and the application layer. And actually DNS is considered another layer on top of the application. So because whenever you request services using HTTP protocols or using any domain name, right? You have to convert the domain name into IP address, right? Because DNS, domain name, is for human beings, right? But the machines are actually communicating each other using IP address, right? So the DNS functionality is to translate the domain name into a IP address, okay? Of course, currently these days, DNS are not only used for translating, domain name to IP addresses, but also being used to many other features for securing emails or securing, the other application protocols. But at this stage, let's just focus on IP address, okay? So when you open your browser, when you type a domain name, the first thing your browser will do is to translate the domain name into IP address using DNS protocol so that you can connect to a machine and you can communicate with the machines for exchanging an email or fetching a content or other application protocols, right? But the same problem happens. DNS was designed at the first stage of the internet invention, so that at the time, just the function itself is the only focus, okay? So at the time, just the only focus was to translate the domain name into a IP address, so any security consideration at the time never made, okay? So because of that, it is plain text protocol, so anyone in the middle of the path can actually snatch the DNS packet and insert the wrong IP address to make the client to connect a different machine, okay? So this attack is so powerful. So I'm not sure how many of you heard about this attack, 농협 phishing attack that happened about nearly 12 years ago. At the time, this DNS was modified to make the users, 농협 users, to connect the different machines to let them show a kind of similar looking website to steal their credentials. So to overcome this limitation, DNSSEC was introduced to add integrity of DNS response. So I'm going to also introduce protocols later this class. Email. You use email every day for sure. So the email is built on the top of the one protocol called SMTP, Simple Email Transfer Protocol, but also no security feature at all. So as time goes by, the lots of security features have been added on top of SMTP, such as SMTPS, StarTLS, DANE, and etc. As you can imagine, you might have noticed, at this moment, the security feature of these protocols, the name itself is very similar looking as the original protocol, right? The name is not totally different thing. For example, HTTPS, HTTP plus S, DNSSEC, DNS plus SEC, right? What it means is we are not changing the base protocol at all, right? We are actually providing a kind of extra layer on top of an existing protocol to support backward compatibility. Okay? So because of that it is so natural that the email, the security extensions to the existing protocol's names are similar looking as the original one. Okay? So routing, BGP. So let's say you connect to a machine. You send you'd like to connect to one machine using an IP address. Then the baseline assumption is there is a path, right? I mean the existing physical path, right? Between you and the communication endpoint that you like to communicate, right? This is done by BGP protocol. There is a bunch of routers between your path, and each router knows whenever it's received a packet, it knows where to forward the packet. Okay, so basically, each router has to know all the paths that toward one destination. Okay? But again, this BGP protocol has no authentication mechanism at all, so it was vulnerable. Still vulnerable, actually. We're going to talk about it later. So to overcome this limitation, RPKI, BGP-SEC, and other bunch of other protocols were introduced to add the integrity. Okay. So, so these four protocols are the things that we're going to cover throughout the semester, this winter courses, right? But one common thing about these protocols is these are relying on public key cryptography, right? Because we are typically, whenever we add a security layer on top of existing protocols, we use cryptographic technique, right? But if you're not familiar with the cryptography, right, I'm sure that you must be scared about cryptography, right? Because it comes with the lots of mathematical notation, but it is fine. Don't be scared, all right? Because we're going to use just the two simple properties that this public key cryptography provides, okay? So again, if you're not aware of cryptography or public key cryptography, it is totally fine, okay? So the public key cryptography needs to have at least two key pairs, right? One key pair, right? Two different keys, which is one key pair. So which is private key and public key. So as you can tell from its naming, private key is the key that only you, the owner, know about, okay? So you shouldn't leak your private key for sure. The public keys, in contrast, as you can tell also from its naming, it is public. It is publicly available, right? But one nice property about this public key cryptography is, if you encrypt something using your private key, it can be decrypted using public key. If something is encrypted using public key, it is decrypted by private key, which is awesome, right? So as you can tell, it is asymmetric key, right? In contrast, if you recall symmetric key, it is a single key which can be used for both encryption and decryption, right? But asymmetric key is different. If you encrypt something using private key, it must be decrypted using public key, vice versa. Yeah. But one thing you should be worth to know is it is much faster to use symmetric key to encrypt something and then decrypt it, right? If you encrypt something using private key and would like to decrypting, using a public key, it is much slower than using a symmetric key. We're gonna recap this properties later again in HTTPS session, but just to know, okay? So using this private and public key pairs, there are two nice things that you can do. The first one is authentication. Authentication is like a signature, right? Basically sign, okay? So whenever you make a contract, you sign a contract in offline world, you use your own signature, right? Make on the bottom of the document, you typically sign something, right? The assumption here is because the underlying assumption whenever you generate your signature on the documents is only you can generate the exactly same looking signature, okay? So, which is authentication in the real world, okay? So, to make a signature, the private key is used to basically encrypt the documents using private key, okay? But of course, if you'd like to encrypt the whole document using your private key, then the size would be really, really large, right? For sure. So instead, what we are doing is we make the documents into really, really smaller pieces, which is hash. We use a hash functions to make the documents be unique, but also really, really, really smaller, right? And after that, using that hash functions, we encrypt that hashed output using private key, and we name it as a signature, okay? So that the other person can decrypt that signature to get the original signatures, and after that, it compares with the original document hash function, right? So in this way, the receiver can verify if this signature is generated by Alice, right? So this property is called authentication, okay? And the other one is called encryption. So as you can tell from its naming, it is typical. It is very trivial. If someone would like to encrypt the document so that only you can decrypt the documents, then what that person can do is to apply that public key to encrypt the documents so that only you can decrypt the documents, right? So what you can remember at this point is there are just the two. There is a public key cryptography, and using nice mathematical formula, there are two good properties that this public key cryptography provides. The first one is authentication, and second one is encryption. Okay. So, but the main challenge here is that, all right, we know that public key cryptography is really nice. It has nice two properties, right? But the thing is, let's say you disseminated this public key, all right? So someone would like to use your public key to verify your signature. Then the whole point here is, if someone fetches your public key, then how can this guy guarantee that this public key is actually from yourself, right? It is really hard to provide that guarantee, okay? That's what this infrastructure provides. If someone fetches your public key, then this guy has to have some guarantees that this key actually belongs to you, right? So that's what public key infrastructure provides. So public key infrastructures only focuses on key distribution and the key identification. So some of you might be confused with, public key infrastructure functionalities to provide authenticity and integrity. No, that's what public key cryptography provides, right? The infrastructure is only to provide the key distribution and the key identification, which means, hey, this key, I can know for sure I fetched this public key from somewhere else, but I know this key is indeed from TJ, okay? So, and the next one is, let's talk about how this public key infrastructure is actually implemented in the real world, in our internet space. There are multiple ways to implement this public key infrastructure, but we usually in the internet rely on hierarchical structure. So what it meant by hierarchical structure is the entity, each person can only trust a set of small trust anchors, right? Because imagine there are billions of the people around the world, and if you'd like to have all the key information in your OS, right, in your computer, it doesn't scale at all, right? It doesn't make sense, right? So instead, each person or OS computer OS needs to trust a small set of public keys. And no matter what, because they are in your trust stores, they believe this key is authentic, okay? Which means if you see some keys from somewhere else, which is not in your trust store, if that key is ultimately signed by one of your trust anchors, then you can trust it, okay? Because this trust anchor signs can generate a signature for other keys, which means the other keys can be verified using your trust anchor, okay? And this key can be also used to generate a signature for other public keys, which means eventually this leaf, right? This green key, we call it leaf key because it is located at the terminal node, right? So this leaf key can be ultimately verified using one of your trust anchors, right? So this chain is called chain of trust, and many secure protocols in your internet rely on this hierarchical structure, okay? So as I mentioned before, throughout this semester winter course, we're gonna learn how DNSSEC works, how HTTPS works, and how email security DANE works, and how routing security BGP RPKI works. These four security protocols actually share the same concept, okay? So if you can understand it thoroughly, the first session of this course, then I'm sure that you can understand the other remaining lectures as well. Yeah? So let's move on DNS. So my underlying assumption is you probably know how DNS works, right? But in case of you're not, let me briefly walk you through what DNS is and how DNS works, okay? So as I briefly mentioned before, DNS is to translate the domain name to IP address, right? So let's say you open your browser, you type example.com. then what you will see is example.com webpage, right? Because the browser is for HTTP protocol, right? But the underlying, before showing you the HTTP content, let's go backward, right? So you saw the web page, right? To see the web page, you have to connect the web server because web servers must have given you the web page, right? Then to go to the web server, you need an IP address, right? That's what DNS does. You type domain name and DNS resolver will try to convert this domain name into IP address by sending a DNS request to example.com's authoritative DNS server. Okay. So I know you might be confused if you're not familiar with these two terminologies, DNS resolver and DNS server, DNS authoritative server. Okay. DNS authoritative server means this is the DNS server that maps all the domain names that you are interested in. For example, example.com's DNS authoritative server, they manage all the DNS records related to example.com. Okay, and what is the DNS resolver? So of course, it'll be better if your browser, if your computer tries to look up the IP address of example.com by itself. But in reality, it's not, right? Because one quick example is, let's say you guys are in the same classroom, right? Let's say all of you try to visit the same website, right? And if you're not using resolver, if you try to look up the domain name by yourself, it means all your computers, let's say there are 50, 50 students are in the same classroom, then 50 students have to go to example.com server to fetch the same IP addresses, which means even though you guys return the same IP addresses, but still you guys need to send the DNS request, right? Which is not efficient, right? So instead, we use a kind of central point, which is called DNS resolvers. And we just ask DNS resolver, hey, no matter what, I'm interested in the IP address of this example.com, right? So the DNS resolver go to the authoritative servers and fetch the IP address and cache it, okay? So that the other subsequent DNS requests for example.com can be returned immediately without contacting the authoritative server again, okay? So DNS resolver return, if it is cached information, it return the IP address to the browser easily, okay? So if you're using, DNS resolver IP address is typically, returned by DHCP protocols. If you don't know about, DHCP protocols, it is fine. So if you're using if you're using the 성균관 University's Wi-Fi network, most of the time, I'm sure that you're using 성균관's default DNS resolver. So all your DNS requests will be handled by the central DNS resolver. But let's say if you're very familiar with DNS resolver settings, so let's say you forced your computer to send all the DNS queries to Google 8.8.8 or Cloudflare IP address 1.1.1.1, right? Then your DNS requests will typically go to the servers and they will handle all DNS queries on behalf of you. Okay? So at high level, in summary, DNS is a database, is distributed database. So example.com's DNS entries is managed by example.com's DNS authoritative servers, and google.com's DNS entries is managed by google.com servers, so which means it is distributed database. So it is very simple client server architecture. It uses a port number 53 for UDP and TCP as well. But TCP always needs to make a connection using a three-way handshake protocol. So to remove that overhead, we typically use UDP, okay? It also has a hierarchical namespace. So if you're interested in the mailgoogle.com's IP address, you first go to the root zone to get the top level .com's IP address. And you go to the .com name server and ask, hey, what is the google.com's name server? And you go to the google.com, google.com again. Hey, I'm interested in the mailgoogle.com. Please let me know the name server in charge of this IP, this namespace. and you go to the mailgoogle.com's name server and get the IP address, right? So that you can go to the web page, okay? So this is the kind of name hierarchy. Root server manages only the top level domain names entries. So for example, .net, .edu, .com, .co, .kr, or .gov, or .org, etc. Okay, and under .edu, there are some other second level domain names such as virginiatech.edu's, mit.edu's, or skku.edu, something like that. Okay. So top level domain names are at the top, and the maximum 3 DAS, which means the number of subdomain names can be up to 128, so that we can this name collision can be avoided. So which means virginiatech.edu, vt.edu, and vt.coms are totally different domain names. Yeah. So okay, let me skip it. Then what is the problem with DNS? Okay, so DNS is, as I mentioned before, when the response comes from authoritative server, it is just a plain text, which means bad guy can insert the wrong IP address to make the browser to connect a different web server, right? Typically, this modified web server maybe showing advertisement or other contents, or exactly same looking original website, just to launch a phishing attack. Okay, so if you're too young, if you're not aware, not familiar with this attack, you can just Google 농협 phishing. Okay, so 농협 phishing DNS. All right, you will see lots of articles regarding that. Okay, then let's see how DNSSEC prevents this problem. Yeah. So now, DNSSEC also uses a public key infrastructure. So now it has a private public key pairs. Okay. So when the request comes in for example.com, now the example.com returns not only the A record IP address, but also returning the signature. Okay. Signature. Okay. So to verify the signature, right, it's authentication, right? Please recall the diagram that I showed you before, Alice signature. To verify the signature, you need a public key, okay? So now, example.com's name servers also provides a DNS key record, which contains a public key, okay? So using this public key information in the DNS key record, you can verify the signature of RSIG records. Okay? This is the part where we cover in the public key cryptography slide. It is same. It is exactly same, right? You go to, that document correspond to this 1, 2, 3, 4 A record, and the signature Alice signatures correspond to the RSIG record, and the public key, the green public key, matches with the DNS key record. Okay. Then the problem is, if you receive the DNS resolver fetch the DNS key, but it has no guarantee still that this public key actually belongs to example.com. That is the problem, right? The problem, right? So now to fix this issue, the public key, DNSSEC uses a public key infrastructure, which is a hierarchical infrastructure. So now .com also has its key pair, public-private key pairs, and use this private key to sign example.com's public key. Okay. Root zone also has a key pairs, so it uses private key to sign .com's public key. As you can tell from its chain, this is also called chain of trust. Okay. From the DNS resolver's perspective, to verify example.com's DNS key, all it needs to have is root public key. Okay. So which is the trust anchor, right? So DNS resolver can verify this DNS key fetched from example.com by verifying by fetching the signature DNS key signature using .coms key, and .coms key will come with the signature, which can be verified using root DNS key, which is fetched already prefetched in the DNS resolver, right? So let's see how this works in practice. So as the assigning process between root from the root to the .com and from .com to example.coms are basically same. So let's focus on the latter one. Okay? So to make the example.com's public key assigned by .com's private key, we have to upload, we have to pass example.com's public key to .com, right? So that .com can use its private key to sign the public key, okay? So to do that, example.com needs to create another record called DS record, delegation signer records, which is just the hash of your public key, which is very simple, right? After that, excuse me, example.com needs to upload this DS record to the .com so that .com can also sign this DS record using .com's private key, okay? So if DNS resolver wants to verify this public key, DNS key, is actually authentic, what it can do is it can go to .com and fetch the DS record and it checks if DS record is matched with hash version of DNS key, all right? Because DS record is just fetched from .com, which is the upper authority, right? And DNS key is just fetched from example.com, right? Again, DS record is just passed by example.com and DS, which is the hash of DNS key. So what this DNS resolver can do is it hashes the DNS key, which is just returned from example.com. It compares with the DS record, which is retrieved by .com, which means if these two records returned from separate entities are eventually same, it means it is verified. Okay, so in a large, overall, high-level picture, what you can imagine is at this moment you can ignore this. Where is my pointer? Sorry. So at this stage, you can ignore KSK, ZSK. I'm going to talk about it later. So a record IP address comes with the signature. It is signed by example.com's DNS key. It also comes with the signatures, right? And which can be also verified using this key. I'm going to talk about it later. And this key, to verify this DNS key, you have to verify the DS record, which is fetched from upper domain name, which is .com, okay? So .com's DS record also comes with the signature, which can be verified using .com's DNS key. To verify .com's DNS key, you can go to the root zone's DS record, compare it, right? And .com's DS record comes also with the signature, right? Which can be verified using DNS key of the root DNS zone, which is prefetched in DNS resolver. So as you can tell, there is a large, number of chains here, but eventually what it says is using a only single, DNS root DNS key, which is prefetched in the DNS resolver. Using this key, you can verify all signatures. Okay, which means each domain name does not need to carry. Each resolver does not need to prefetch all DNS keys at all. Okay, just one single key, root DNS key, solves everything. So as you can tell, it is a hierarchical PKI. So each resolver, and now in this diagram, the person is not a end host, it is actually DNS resolver, right? So each DNS resolver needs to have only one, needs to cache only one root DNS key, okay? And after that, if the example.com one random domain name comes with the signature and the DNS key, you can verify the DNS key by checking the DS record and the parent's DS record. And if that DNS DS records and the DNS key eventually can be verified, right, using DNS resolver's DNS key, then all the verification is done. Okay, so this is the quick summary slide, right? The sender, DNS authoritative server, okay? DNS records, IP address, right? The sender first apply hash function, okay, to reduce the size of DNS record, okay? And after that, it encrypts this hash record to generate a signature, which is in the RFSig type of DNS response, okay? And after that, the receiver, DNS resolver, fetches two information. The first one is DNS records, IP address, and also it comes with signature. Then what the receiver needs to do is to verify if this signature is authentic, okay? So to do that, first, uses its public key to decrypt the signature, which explores the hash of DNS records, right? So now you have hash information based on the signature you received from the sender. Now you can do the same thing using the DNS records, which is IP address, you just fetch it, right? You apply the same hash function the sender used, right? The assumption is receiver knows which hash function the sender has applied. Yeah, apply hash function, get the hash of the DNS records, and after that it computes. If these two records are same, right, it means it is authentic. Okay. So let me pause a 1 minute here so that you can double check your understanding, right? So if you're not sure about this concept, please feel free to shoot me an email, right? tj@virginiatech.edu. Okay. So let's move on. So this is the kind of advanced version. So if you're not familiar, if you can't understand that, it's fine. Okay. So I just mentioned that the A record uses a private key to generate a signature, and the DS record is a hash of a public key. But the thing is, these two keys are different, right? So there are two types of DNS key. One is called key signing key, and the other one is zone signing key. Zone signing keys are used to generate a signature, right, to sign the DNS records, and the key signing key is only used to generate a signature for DNS key records. Okay, so A record, A record, NS record, DS record for all the other records except DNS key records. The zone signing key is used to generate a signature, and the DNS keys also carries a signature. To generate a signature for DNS key records, we use a key signing key. Okay, let me tell you why. So let's say, think about the zone signing key. There are the DNS authoritative servers manages a lots of different DNS records, and sometimes their records updated frequently, which means zone signing key has to be used whenever you change your DNS records to generate signatures. So for the fast for performance reason, this zone signing key has to be used frequently, which means it is better to put that on the memory, right? But in the security perspective, something in the memory is generally considered insecure, okay? But instead, key signing key is only used to generate a signature for DNS key records, okay? So technically, it is not a signature of GSK, it is DS and DNS key records, but anyway, which means Because key signing key is only used to generate a signature for DNS key records, which means it is not that often used comparing to the zone signing key. Okay, so it doesn't need to be heavily used, so that it can be stored in the offline storage in much more secure place. Right. So in the worst scenario, zone signing keys can be leaked. Then it's fine. You can you can introduce a new zone signing key. You can just load a key signing key, which is not stolen, and generate another signature, right? Zone signing key, of course, it can be cached in somewhere, but it will be, evicted after the TTL, so that the attack vulnerability window is much smaller than just using a single key to sign everything. Okay. So when you see a kind of visit the three principles of internet information security, confidentiality, integrity, availability, and as you can tell, DNSSEC does not provide any confidentiality because its sole focus is integrity. Okay. So let me show you one demo, real quick. So if you're using DIG is domain name indication grouper tool, you can quickly send a DNS request to a target server so that you can take a look at what the DNS response looks like. So if you're using macOS or Ubuntu Unix system, I guess DIG just command will be just working. Okay. So let's say I'm interested in one domain name such as Cloudflare. All right. And I'm interested in a record, which is the IP address. When you type this IP address comes, all right? Then let's say I am sending the DNS request to Google DNS resolver. So what I'm doing here is I'm asking, hey, Google, I'm sending DNS request to Google DNS resolver, and it says, hey, I'm interested in cloudflare.com's IP address, okay? And the IP address comes, right? Then I might be interested in, hey, I'm also would like to see how the signature looks like. So what you can do is you can add an option plus DNSSEC, which show you a signature. Okay. Then this becomes each field has a different, of course, each field has its own structure. So for example, this key signature is only valid, from December 8 to December 10, right? So these signatures has a validity period. If the signature expires, then it is automatically invalid. Okay, and this is called key tag. So there can be lots of DNS keys. So this key tag can be used to find the correct key to verify the signature. So let me show you one example. So multi-line. This is just for cosmetic things, right? So let's say this key is signed by key tag, the key of which key tag is 345, right? So to verify this signature, what do you need is DNS key record. So I'm asking DNS key record, and DNS key record comes. 256 means it is key signing key. 256 is the zone signing key. The key ID is 34505, which is the same as this key. Okay, so if you really would like to verify the signature, what you can do is you can download. You can get the signature, and also using this DNA records and make apply the hash function, and after that, you have to compare the hash erasers with decrypted signature using this key ID. Okay, that's what you can do. And as you can tell, this DNS key records also comes with this signature. Okay, so this DNS key is signed by 2371, which is the same as the key signing key. Okay, so. And if you'd like to compare with the DS record, then you can ask, hey, I'm interested in the DS record. And the DS record is the key is 2371, which is matched with the key signing key. Okay. but this DS record is signed by .com's private key, which is 53929. So you can also fetch the .com's DNS key, right? Which is the zone signing key is 53929, which is matched with this signature DNS key, right? So as you can tell, what I'm just to show you is Cloudflare A record is fine. Zone signing key, the DNS key records that contain both zone signing key and key signing key is signed by key signing key, and key signing keys DS record can be found in the .com's game server, right? So I just create a one chain, right? So that you can do the same step to verify .com's DNS key by fetching root zone's DS record. Okay. Yeah. So so far we focused on the quick concept of DNS key, how DNS and how DNSSEC works. So in the next chapter, we're gonna talk about how DNSSEC is used and deployed over time, and DNS, what is the current limitation and the challenges of DNSSEC ecosystem, right? All right, thank you so much, and we'll see you at the next class. All right, thank you.